Hello, I'm Robert Smith with Oak Ridge National Laboratory, and I'm here to talk to you today about the Eclipse Advanced Visualization Project, which is an Eclipse Foundation Science Working Group project for integrating scientific visualization software into Eclipse Workbenches. So, we'd love to talk about Eclipse a little bit. You're probably already familiar, but it's an IDE, one of the most popular ones in the world. It is based on OFGI for providing services and packages, and this is important for extending Eclipse, which is what leads to the ideal of the rich client platform, which is using the Eclipse's code base to create your own custom workbenches. And in our case, we wanted to create a scientific workflow, and you might think, well, why would you choose Eclipse for scientific workflow management? Well, the scientific workflow can go from everywhere from writing code to running simulations to pulling back and visualizing and analyzing the data. And that's where Eclipse really comes in, because with Eclipse, you can use the normal, I guess that's still readable, but, okay, there we go. Thanks. So with scientific workflow, and what we did was we created the Integrated Computational Environment, EIF, which is an Eclipse RCP. And using EIF, you could use Eclipse's programming IDE to write your code. Then you could create a model builder that would have a graphical interface that could create and verify your input model file. And then you could also create a job launcher, which would launch the program you wrote using the model file you created. And this could be either on your own machine or remotely. And then finally, once it's done, you could pull back all of the data and you could analyze and visualize it. But if you think about it, that isn't really the only reason you would ever want to have a visualization inside of an Eclipse workbench. So what we did was we took all of the visualization code from within EIF and we spun that off into its own Science Working Group project called EAVP. And that is what had the history of exactly what motivated this. So, a little bit about the architecture of the, yeah.
Is it bound to any particular version of RCP, like 3.x, 4.x, or can it be used in both versions?
I'm not aware of anything that would, off the top of my head, that would break if you used it in RCP 3. I don't think I've ever tried it, but.
So your use case is RCP 4?
Yeah.
Cool. That's awesome. Correct. Okay.
So basically, every type of visualization that we offer is implemented as its own bundle within OFGI, or a hierarchy of bundles if you have more than one implementation of it. And each one contains a iViz service, which is an OFGI service that can be consumed. You can also use these via Eclipse extension points. And basically, the RCP app will select the visualization you want from within the ones offered by EAVP, and then we also have a way to configure it through the preferences menu if that's necessary. So, going through what we have in EAVP, our most basic case would be 2D plotting for graphs. Basically, you run something, you have some data, you want to see a graph of it. So we use a XYZ plot for the implementation. Basically, we take in a CSV or a DAT file. We will automatically try to detect the delimiter, and then we will plot it on a graph and put that into the Eclipse Workbench. So this might, so we'll have a variety of controls. You could, for example, change what series are being plotted, what's being plotted on the axes, the colors, zooming, taking screenshots, this kind of thing. And we also have in another tab the text file itself, which in case you want to edit or just create a text file from a data file from scratch. So here is a screenshot of that working in ICE, and as you can see, we've got the product, the file we're opening, and just a basic graph there. But a little bit more interesting is the Vivid or ParaView. These are third-party programs. They're really kind of state-of-the-art. I believe ParaView it is that has the world record for the largest scientific visualization. They're both open source. Vivid is out of Lawrence Livermore National Laboratory. ParaView is from Kitware. And as I said, they're both very robust, very efficient. They work on in a HPC environment and can cover a very large number of cases. This is a small sample of the data types. So if these are third-party software, these are not integrated into EAVP. You have to download them separately because we don't necessarily require that they be on the computer you're trying to visualize on. You may want to run your visualization on a remote machine, such as an HPC computer, and in that case, you can set up your connection to a remote or to a local instance. So basically, once you have that set up and you've given EAVP all the information needed to open the program, what it does is when you try to access it, it will launch that connection, open the program, and then just run it in the background and use it as a backend. So when you try to open a file, it will pass the file along through the connection to the third-party program, and then the program will create a visualization as normal for it, and just pump the pixel back to ICE so that it can be put into a SWT composite. And we use the mouse motions to do things such as controlling the camera, just as you would if you were using any of these natively. And then we also offer some UI pieces to can have more full control. So for example, you might reset cameras, things like opening up ParaView's web visualizer in case you want to spawn one of those. You can, within EAVP, create the web visualizer and then look at it within a browser within ICE, or you can use whatever your browser of choice is outside of Eclipse if you like. Another thing we do here is Vivid has a very robust Python scripting engine that allows you to have a great deal of control over the model that you're visualizing. And basically what we will do is we have a button that it will pop open a cell, and within that you can just type in whatever script you want, load it from a file, and then just send that directly to the Vivid instance. So here we have ParaView and Vivid running within Eclipse. On the left we have a will open in ParaView, and on the right a battery in a heating simulation within Vivid. So the third kind of category here is we don't just want to use third-party programs. We want to be able to offer our own visualization for custom use cases. So we turn to JavaFX, which has a basic 3D rendering engine within it. This isn't really professional, like bleeding edge kind of thing, but it is sufficient for our needs because we aren't doing some kind of video game here. We have some scientific data, and we just want to sanity check it, or to look at it to detect, irregularities, or so that the domain scientists can see exactly with the output of their simulation lines up with what they were expecting. So we use EAVP Eclipse to integrate it within Eclipse. Basically, we have an FX canvas that will transparently forward all user interactions over to the JavaFX scene that is displayed within the FWT canvas. And that will allow basically complete control over it as if you had it within a JavaFX native program. You can do picking, camera control, that kind of thing. So we have two different mesh editors within, 3D editors within EAVP. They both have only JavaFX implementations at the moment, but we have it so that the rendering engine is able to be easily swapped out so that in the future we can have other implementations. So the first of these is the mesh editor. This is for 2D mesh editing. So our main use case is for NEC 5000 fluid dynamics simulation. And that informs a lot of what we have right now in it. You can basically use mouse clicks to create your mesh, and then you can click and drag the mesh around to edit it. Or within the Eclipse properties view, you can do things such as set exact coordinates for your points. And also, you can have properties on edges, points, or polygons. And right now, as I said, these are mostly these are mostly devoted to fluid dynamics boundary conditions, but in the future we'll be able to have arbitrary amounts of arbitrary conditions on any of them. And here is a screenshot of the mesh editor in action. You can see the blue highlighted polygon. You can see the grid, and at the bottom here, you can see some of our conditions for the fluid dynamics problem. These are all editable. And then our second case is the geometry editor, which is 3D meshing. So it uses constructive solid geometry in order to have multiple shapes on the screen at once. It does, the CFG function isn't terribly complex, but it's mostly, so our main use case is visualizing files. So in that case, we have a variety of files supported. Each of these is done through a domain-specific language written with Xtext. And each of those is provided to the geometry editor through extension points. That makes it very easy to add new file types to it as the need arises. You just create your DSL in Xtext. You implement a simple service, and that basically puts it in. So the mouse is used to control the camera and for picking, which allows you to see a shape's properties in the properties view. And shapes can have a variety of properties based on the scientific data associated with them, and also with the graphics. So we can also edit the mesh in real time. So if you want to view the explicit mesh data of every point on every triangle, you can do that and change it while you're looking at your file. We also provide a variety of decorators for each shape in the data structures that we have written for the geometry. So for example, here you can see a slot machine. This is all read in from a single file, so that is why it is automatically created as a composition of each individual shape from within the file. And you can see you can change the center to move them about the space, and you also can see the UI decorators. So in this case, you can have color, scale, and here we have set the entire thing to display as wireframe, and each of these can be toggled on or off so that as you go down the hierarchy, you can decide which piece is in control of the display. So in here we have the entire thing set to wireframe. If we wanted, we could turn that off and set each individual piece to wireframe, to solid, or etc. And here is just a look at what things look like in solid mode. We've got a drill bit, a clamp, and another thing all in the same scene. So how do you actually use these? You basically take the file or data you want to visualize, and you get the IVIS service that you want, and each IVIS service publishes a list of data type of file types that it can handle. You basically find the one you want, and then you pass the file through the create canvas or create plot method. The difference here is that create canvas is more for editors where you're actually creating or modifying the data, where it says such as the mesh editor and geometry editor. The create plot creates an iPlot, which is more for Vivid ParaView, things where that are devoted purely to looking at the data. And then you just draw it to an arbitrary composite, and you have your visualization right there ready to go. So, and then we also have the preferences menu, wherein we can set up the connections to our third-party programs. We can support both local and remote connections. We make use of the Parallel Tool platform to inform a lot of our connections properties. So for example, if you set up a PTP connection to a remote machine to launch a simulation, and then later you want to do a visualization of that of the data you got from it, you don't have to go through and set up the same connection twice. You can take most of what you need from PTP straight. So you can also have these set to connect automatically on startup if you're going to be using this workbench to work this kind of visualization over and over again. So here is a screenshot of our preferences menu. You can see how you just set the connection you want, define on the port you want for the connection, and point it to the program you want to launch. And once you've done that, you're ready to visualize. So where do we want to go in the future? One of our main goals is to look at what else can we put this in. Can we put this in we've got this working in SWT composites. Could we put this in Swing? Could we put this on the web through a JavaScript? Can we put this into a backend window? And we also want to look into creating additional implementations. Right now, JavaFX is kind of limited. We used to have a JMonkey implementation of these. We ran into Eclipse Foundation IP issues there, but we would like to offer that in a marketplace as another option. Again, in the future, we are also looking at in situ visualization. The idea there is that you don't necessarily want to wait until your simulation is complete before you can see some data. If there's something wrong, you want to be able to catch that as quickly as possible so that you don't waste your time finishing off a simulation if you could look at it at, say, 10% done and say, oh no, wait, something's gone wrong here. Let's back off and stop wasting our building time on, Titan. So we're looking into using audio to do that. We also want to do some volumetric mesh editing. So right now we have the 2D mesh editor. It would be nice if we could use that, if we could extend that into the third dimension so that we could have meshes that have volumes instead of just polygons. And the use case there is we would like to, instead of just having our fluid dynamics problems, in the future we would like to be able to, extend that to a finite element support so that any finite element problem can be expressed and viewed in EAVP. So just finishing up here, we have the product page. We've got a repo. We are open source, of course, and I've got a small tutorial just for a beginner who is new to OFGI and wants to see what the correct way to set up a service is to get that into their program and really expedite the process of getting the service working. All right, so I'm going to now open this up to questions. Anybody? Okay then, thank you for coming.